it's not just on the border. This is Fort McMurray burning this afternoon.
Signs are all there, with fires raging around the world, in Greece and Turkey and in California.
And 2025 marks 3 years above 1.5 degrees.
The fire seems to be burning across the highway.
Hectares early this morning, but as I mentioned, it exploded in size over the span of 24 hours. It's actually now over 100 times larger than it was.
There is a magic machine that sucks carbon out of the air, costs very little, and builds itself. It's called a tree.
We are Group 7, and for our APSC 171 final design project, we engineered a proactive solution, a fire risk monitoring drone. Currently, early detection relies heavily on satellites or stationary sensors, which may miss localized high-risk zones. We see firsthand how rapidly these fires can devastate communities, such as the McDougall Creek wildfire right here in Kelowna. Our mission was to design a low-cost, unmanned aerial drone capable of monitoring remote environmental conditions to identify regions at high risks of wildfire, enabling preventative action before fires occur. Because this drone is intended for remote, forested areas, my specific focus was designing landing gear to absorb impact and keep the underslung sensor safe.
With the drone safely off the ground, we needed to ensure it could stay in the air efficiently. I was responsible for designing the propellers. To carry our battery, frame, and sensors, the total thrust must exceed the weight of the drone. We aim for a thrust to propeller ratio of 2:1 to ensure stable flight even in unpredictable winds you might find near a high-risk fire zone. We carefully sized the propellers to maximize power and propeller efficiency so that the drone can maximize its time spent monitoring the forest.
As airborne, our drone executes its primary mission. When a fire alert system identifies a region of concern, the drone is deployed to the target area to collect real-time data. Sensors measure humidity, temperature, and other data, which is transmitted to the ground station. Our system evaluates the fire risk by calculating a localized hazard score using a specific formula. Risk score equals temperature times 1 minus humidity. This allows authorities to take preventative measures.
To house the brains of this operation, I designed the central frame and electronics holder. A major engineering constraint was ensuring that the volume of each 3D printed part should not exceed 250 centimeters cubed. The central frame acts as a chassis, safely housing our core avionics, including the Arduino Nano, the MPU 6050 IMU, a 4-in-1 ESC, and a 40-gram LiPo battery. The electronics holder keeps everything secure while maintaining necessary airflow.
Connecting the propulsion to the frame are the arms, which I designed. The arms are the primary load-bearing structures of the quadcopter. They need to be rigid enough to prevent vibrations from reaching the MPU 6050, which provides gyroscope and accelerometer data for stabilization. Any flex in the arms could throw off the flight controller, so structural integrity was critical here.
At the end of the arms are the motor mounts, which were my focus. These mounts are engineered to securely hold our 4 5200 kV brushless motors. Because our drone is designed to carry a payload of environmental sensors, these mounts are structurally optimized to handle the high torque generated by the motors. We utilized M2 screws to securely fasten the assembly, ensuring perfect alignment.
At the heart of the drone is an Arduino Nano acting as a flight controller. It reads orientation data from an MPU 6050 gyroscope and accelerometer, which tells it exactly how the drone is tilting at any given moment. Using that data, it runs a PID control algorithm that constantly adjusts the speed of each motor to keep the drone stable and level. The 4 brushless motors are controlled through a Flycolor Raptor BLS04 4-in-1 ESC, which receives PWM signals directly from the Arduino on pins D5 to D8. The ESC then converts those signals into precise power delivered to each motor. For wireless control, the drone uses an NRF24L01 transceiver communicating with a custom Hana Mechatronics remote controller built around an Arduino Pro Mini and 2 joysticks. Throttle, yaw, pitch, and roll commands are transmitted wirelessly and received by the drone in real time. The drone also features a DHT11 temperature and humidity sensor, which serves as the project's primary data collector. As you can see here, it's reading live environmental data and displaying it accurately on an LCD screen. To demonstrate a real-world application of our drone sensor data, we designed a simple fire risk monitoring website. Using an open-source map of the Kelowna area, the surrounding forests and parks are divided into regions. On the right-hand side, temperature and humidity readings collected by the drone can be logged for each region. Those values are then run through a risk index, and that region is color-coded on the map. green for low risk all the way up to red for extreme, giving a quick visual of which areas are most vulnerable to wildfire.
Wildfires move fast, but with our drone, our response can be faster. By combining scalable 3D printing, accessible electronics, and predictive environmental monitoring, we believe our design offers a smart, marketable solution to one of our region's most pressing challenges.